In this lecture, I'm going to explain to you why Gaussian integers form a Euclidean domain. Recall that Gaussian integers are uh, the ring of Gaussian integers denoted by z square brackets I is a set of all complex numbers of the form a plus bi, where a and b are integers. And addition and multiplication in Gaussian integers are inherited from addition and multiplication in complex numbers. So a plus bi times c plus di is just ac minus bd plus ad plus bc times I. Okay, and what I want to explain is that Gaussian integers form a Euclidean domain. Okay, obviously Gaussian integers form an integral domain because it's a subset of the complex numbers, and if you multiply two non-zero complex numbers, you still get a complex number. But why do they form a Euclidean domain? So in order to show that integral domain is a Euclidean domain, you need to give a size function. So let's define the size function. Define d of a plus bi to be a squared plus b squared. Okay, recall that if I take the square root of this, then it's just the absolute value of the complex number a plus bi, which is nothing but the distance of this complex number a plus bi from the zero vector in the complex plane. Okay, and now what I need to show to establish that this is a Euclidean domain is need to show that for all mn Gaussian integers, there exist Gaussian integers q and r such that n is equal to qm plus r and dr is strictly less than dm. Okay, and this is essentially a geometric argument. So what to understand this, what we do is, firstly you fix m. Okay, so in the complex plane you can think of m as a vector. So you have 0 and then you have the vector m. So the complex number m, and you can think of, you can draw a vector from 0 to m. Okay, and consider the lattice L equal to qm, where q belongs to the Gaussian integers. Okay, another way of thinking of this lattice is you consider the vector m and then you consider the vector I times n, so m multiplied by the complex number I, and that's usually a rotation, that's a rotation of the vector m counterclockwise by 90 degrees. So we get Im looks something like this. And this lattice L can be written as AM plus BIM, where A and B are in Z, just because every Q in the Gaussian integers of the form A plus BI. So geometrically what this looks like is, it is sort of it's a square lattice. So it's going to consist of all vectors like this, which form a square grid. A square grid, and the size of each square is just square root of dm. Okay, now I claim that for every n in Zi, there exists Q in Zi such that d of n minus qm is less than dm. So if we can find such a q, then we can just take r to be n minus qm, and we would have proved the Euclidean property of the Gaussian integers. Okay, so actually this is a very geometric proof. In fact, I claim that every complex number inside a square lies inside one of the squares of the lattice L. Okay, so here I'm thinking of, okay, so L is actually a set of these corner points, and I'm thinking of them as being the corners of squares in a square grid. And what I'm saying is, of course, every point in the complex plane lies inside one of these squares. Okay, so we have this, I'll just rotate the square. So we have a square like this. We have this vector is m, this vector is im, this vector is again m, and this vector is im, and one of those squares of the lattice will contain our point z. And so how far must z be from one of the corners of this square? So these are points in L, and each point in a square of size, so what is the size here? The size here is square root of dm. Okay, now each point in a square of side square root dm cannot be more than a distance square root dm by 2 from one of the corners. In fact, the worst point is the point right at the center of the square, and that's a distance square root of dm by 2. And every other point must be a smaller distance from at least one of the corners of the square. So what we have is that there exists qm belonging to L such that z minus qm, that's the distance from z to qm, is less than square root of dm by 2, or in other words, d of z minus qm, well, it should be less than or equal to, here is less than or equal to dm by 2, which is strictly less than dm. So in fact, every complex number is close enough to one of these lattice points. It's within a distance dm of one of these lattice points. And so in fact, every n in Zi, let's say like this, for every n in Zi, there exists q in Zi such that r defined to be n minus qm has dr less than dm. So n is equal to qm plus r, where dr is less than dm. That establishes the Euclidean property of the ring of Gaussian integers. And from this you can conclude that the ring of Gaussian integers is a principal ideal domain, for example.